Welcome to this presentation, which features some highlights from a paper which I posted online titled Predictions for Elementary Particles and Explanations for Data about Dark Matter, Dark Energy, and Galaxy Formation. Our work may help resolve problems, some of which are at least a century old, regarding elementary particle physics, astrophysics, and cosmology. What elementary particles remain to be found? What is dark matter? What is dark energy? This work features theory that describes elementary particles and other objects without emphasizing theories of motion. The work includes a way to add aspects of motion later. The theory outputs descriptions for elementary particles, dark matter, and dark energy. The work offers explanations for data about dark matter, dark energy, and galaxy formation. The mathematics-based modeling has bases in solutions to equations that feature mathematics for isotropic quantum harmonic oscillators. Compared to traditional physics, a first part of the modeling suggests new elementary particles, a description of dark energy forces, and a description of some dark matter. By assuming that nature embraces 6, or possibly 36, isomers of the known charged particles, the work includes another form of dark matter and explains observed ratios of dark matter effects to ordinary matter effects. This table shows results regarding elementary particles. Results regarding long-range forces come from the same modeling basis as do results for so-called basic particles, but do not show well in this table. The second column shows spin. The rightmost 4 columns show particles. Generally, particles for which little sigma equals -1 occur in today's universe in hadron-like particles and atomic nuclei. Particles for which little sigma equals +1 correlate with the term free-ranging. Later, we discuss why it is appropriate that the 3 neutrinos, or 1n particles, have 0 rest mass. Aspects of this presentation feature the 6 1r particles and various components of long-range forces. Later, we repeat this slide and discuss each type of basic particle. The known components of the spin-1 long-range interaction include a monopole interaction that correlates with charge, a dipole interaction that correlates with nominal magnetic dipole moment, and a quadrupole interaction that correlates for an electron with Larmor precession and, for the Earth, with a lack of alignment between the axis of rotation and the axis of the magnetic field. This result is appropriate because, as yet, there is no modeling for translational motion. We discuss a role for 2G68 later. The known, or monopole component of the spin-2 long-range interaction is attractive and correlates with familiar gravity. The 2 octopole components are repulsive and drove the early increase in the rate of expansion of the universe. The featured quadrupole interaction is attractive and was responsible for the multi-billion-year slowing of the rate of expansion of the universe. The featured dipole component is repulsive and is responsible for the current increases in the rate of expansion of the universe. Each of these components, 1 correlating with gravity and 4 correlating with dark energy forces, plays roles in galaxy formation. The 2 spin-4 octopole components do not conserve in interactions, fermion generation, and thereby explain neutrino oscillations. The 2 components also explain astrophysics observations that traditional physics correlates with supposedly non-zero neutrino rest masses. The dipole components, 4G26, 6G24, and 8G26 correlate with the traditional physics notion of anomalous magnetic dipole moment. To explain the observed 5+1 ratio of density of the universe of dark matter to density of the universe of ordinary matter, we assume that nature embraces 6 isomers of charged elementary particles. Each isomer correlates with its own isomer of spin-1 interactions with charge and nominal magnetic dipole moment. One isomer of charged elementary particles correlates with ordinary matter. The other 5 isomers of charged elementary particles provide for most dark matter. The remaining dark matter consists, possibly essentially entirely, of hadron-like particles that feature gluons and the zero mass, zero charge analogs to quarks. Such hadron-like particles would be similar to known hadrons, such as the proton and neutron, but would not interact much with the spin-1 long-range force. We assume that one isomer of gravity spans, or interacts with, 6 isomers of charged particles. From there, our math-based modeling suggests that the component of dark energy forces that now dominates for large-scale effects has a span of 2 isomers of charged particles. This means that this force component has 3 isomers, each of which, in effect, connects 2 isomers of charged particles. The other components of dark energy forces have spans of 1 isomer of charged particles. The precessing quadrupole component of electromagnetism includes interactions between ordinary matter and 5 isomers that are not ordinary matter. Later we discuss a role for the 2G68 component of spin-1 long-range forces. Early in the history of the universe, baryon acoustic waves and dark energy octopole repulsion disperse stuff. Then, quadrupole dark energy attraction catalyzes the formation of single isomer clumps of stuff. Each single isomer clump repels, via dipole dark energy repulsion, stuff correlating with one other isomer. Based on monopole gravitational attraction, clumps correlating with 1, 2, or 3 isomers form early cores for galaxies. The galaxies then accumulate via monopole gravitational attraction nearby stuff. Observations show that the earliest visible galaxies contain essentially no dark matter. We think that these galaxies had cores consisting essentially only of ordinary matter. Some galaxies have about 4 times as much dark matter as ordinary matter. We think that these galaxies formed around ordinary matter cores or around dark matter cores that did not repel ordinary matter. One galaxy has comparatively few ordinary matter stars. We think that this galaxy had a core that repelled ordinary matter. We know of some other galaxy-centric data. As far as we know, our theory is not incompatible with the data. Our theory offers a possible explanation for the Markarian 1216 galaxy, which apparently stopped growing about 4 billion years after the Big Bang. We think that this galaxy had an original core that featured 3 isomers of charged particles. Dipole dark energy repulsion drove stuff away from the neighborhood of the galaxy. As far as we know, our theory is not incompatible with observed data regarding galaxy clusters. The experiment to detect the global epoch of reionization signature, or edges, measured twice as much depletion of cosmic microwave background radiation as people had expected based on hyperfine interactions with hydrogen atoms. Our work suggests that the 2G68 component, which has a span of 2, of spin-1 long-range forces, correlates with the depletion interaction and with the notion that half of the observed depletion correlates with a non-ordinary matter isomer of charged particles. This slide re-shows an earlier table. One topic that we have not addressed is the possibility that nature embraces 36 isomers of charged elementary particles. The possibility correlates with the notion that the span of 6 for monopole gravity might be orthogonal to the span of 6 for quadrupole electromagnetism. For the purposes of this presentation, the main significant consequence would be an additional possible explanation for the non-zero density of the universe ratio of dark energy to dark matter plus ordinary matter. Above, we offered somewhat specific descriptions for new elementary particles, dark energy forces, and dark matter. We used those descriptions to explain observations regarding dark matter, dark energy, and galaxy formation. Our research includes results and methods that we did not discuss above. One source of some additional information is the appendices that follow immediately. Another source of additional information is the paper, Predictions for Elementary Particles and Explanations for Data about Dark Matter, Dark Energy, and Galaxy Formation, which you can find by searching online. We provide additional information about our research. Our research suggests that nature links the ratio of the masses of two elementary particles, the tauon and the electron, to a ratio of a strength of electromagnetism to a strength of gravity. Our theory correlates with, at least approximate, relationships between the squares of masses of the three known non-zero mass elementary bosons. We also suggest a formula that links the masses of charged leptons, the masses of quarks, and the fine structure constant. We discuss each of the types of basic particles to which this slide alludes. We discuss the basic particles for which little sigma equals +1 and the mass is greater than 0. The 0H particle is the Higgs boson. The three 1C particles are the three charged leptons, the electron, the muon, and the tauon. The two 2W particles are the two weak interaction bosons, the Z boson and the W boson. We discuss the basic particles for which little sigma equals +1 and the mass is 0. The 0I, or so-called I particle, is a suggested zero mass relative of the Higgs boson. The three 1N particles are the three neutrinos. We discuss the basic particles for which little sigma equals -1 and the mass is greater than 0. The 0P, or so-called pi particle, might correlate with an attractive component of the strong residual force. The 0P particle might provide an aspect for alternative modeling regarding interactions between hadrons in atomic nuclei. The 6 1Q particles are the 6 quarks. The two 2T, or so-called tweak particles, are analogs to the weak interaction bosons. The charge of the one non-zero charge 2T particle is 1/3 the charge of the W boson. The non-zero charge tweak particle may have played a role in the creation of baryon asymmetry. We discuss the basic particles for which little sigma equals -1 and the mass is 0. The 0K, or so-called cake particle, might correlate with a repulsive component for the residual strong force. The 0K particle might provide an aspect for alternative modeling regarding interactions between hadrons in atomic nuclei. The 6 1R, or so-called arc particles are zero charge, zero mass analogs of the 6 quarks. Hadron-like particles made from arcs and gluons contain no charged particles and measure as dark matter. The 8 2U particles are the 8 gluons. This slide contrasts our efforts to develop our theory with some other societal endeavors. The term small data techniques correlates with the use of just a few formulas or methods. We use the term concepts uniting some physics to refer to our work. This slide and some subsequent slides show the table of contents for the paper, predictions for elementary particles, and explanations for data about dark matter, dark energy, and galaxy formation. Regarding each of these slides, please feel free to pause the presentation to read details. This slide features Section 1, Introduction. This slide features Section 2, Methods. This slide features Section 3, Results. This slide features the beginning of Section 4, Discussion. This slide features the rest of Section 4, Discussion, and also Section 5, Concluding Remarks. Thank you for viewing this presentation. You can find the paper, Predictions for Elementary Particles and Explanations for Data about Dark Matter, Dark Energy, and Galaxy Formation by searching online.